Alright, in this video we're going to go over the AP Calculus AB free response question number 3 from 1999. So in the first question, they're asking us to do a midpoint Riemann sum for subdivisions equal length of this function here. So here's the data for R of t, and we're going from 0 to 24, which is the entire table here. So first thing I'm going to think about is, okay, if I'm going to cut it into 4 chunks of equal length, well, overall, my interval is from 0 to 24, and I'm going to divide that into 4 chunks, so that means each one is going to have a length of 6. Oops, not what I wanted to do there. That's all right. So each one's going to go from have a length of 6. So if I kind of think about that, I'm going to go from 0 to 6, and then from 6 to 12, and then from 12 to 18, and then from 18 to 24. And so then I have these midpoints here of each of those: 3, 9, 15, 21. And when we have a midpoint sum, or a left endpoint sum, or a right endpoint sum, that's telling us what x coordinate or input coordinate are you going to plug in to find the height of your rectangle. So basically what I'm doing then for part A is my first rectangle is going to be R of 3. That's how I'm going to find the height, and that's going to go from 0 to 6, which is of course then a width of 6. Plus my next one from 6 to 12, but to find the height I'm using the midpoint, so that's R of 9 times a width of 6, plus again then R of 15 times 6, and then, sorry, running out of room, plus R of 21 times 6. And of course, I could have factored out the 6 for all of those, but I wanted to write it as a rectangle so that we remember, okay, what we're doing is we're actually just finding the area of a rectangle. Midpoint to find the height, and then what's that width? And then you'll just add all that up, do the actual computation there, and I believe your answer will be 258.6. Now, let's think about the units and then what this actually means. So because my R of t, those are all in gallons per hour, and then my t, which is 6 here, is in hours. I have gallons per hour times hours, which is just going to give me gallons. And what does that mean? Well, since R of t is the rate at which water flows out of the pipe, we're going to say, okay, this represents 258.6 gallons in total flow out of the pipe we're going to say on the interval from 0 to 24. Okay. So that's how we would do that one. That's what our answer would mean. Part B, is there a time where R prime of t has to equal 0? There's a couple different ways to do this. The way that I like to think about it is, well, usually when we think about the derivative being 0, we're thinking about critical numbers for finding local maximums and local minimums. So what I want to see is there a place where R of t changes either from increasing to decreasing or from decreasing to increasing, where we have a relative max or a relative min, because I know usually that means the derivative is equal to 0. And if we look at our output values here, we're increasing until right here, and then now we're decreasing the rest of the time. So I'm assuming that there's going to be a place where we're increasing, R of t is increasing here, and then we start decreasing. Sorry, my stylus maybe needs a charge here. Which usually means that there's going to be then a derivative of 0. Now, of course, there could be a cusp there, or maybe there's some other sort of discontinuity where the derivative never actually equals 0, but we just change. However, it says that r is differentiable. So that's not allowed. It has to be a continuous curve here with no cusp or vertical tangent line. So we can just explain that. So we will say yes, because r of t changes from increasing, need a little more room here. I switched to writing with my finger because my stylus seems to be out of charge. From increasing to decreasing, and r is differentiable. So those two facts together guarantee that there has to be a place where the derivative equals 0. Now again, there's other ways to do that. This is the way I prefer. Also super important, if you don't include this and r is differentiable, you will not get the point for that question. All right. I'm going to go ahead and get rid of all this, give myself some room to write part C. So if you need to pause, kind of catch up on that, go ahead and do that. Now in part C, it says the rate of water flow can be approximated by this function. So they gave us these values that are also the rate of water flow, but now they're saying, well, in addition to this table of values, we also can use this function. Now the function is approximation, where the values are exact here, taken as a measurement every 3 hours. So it says use Q of t to approximate the average rate of water flow. Well, anytime they're asking about an average rate of change, I'm thinking about one of two things. I'm thinking, well, average rate of change is just the slope of a line connecting 2 points, or I'm thinking I have that formula using an integral that gives me the average value of some function. And it all depends on what information I have. If I have sort of the basic equation, the amount equation, then to find the average rate of change, you use slope. But if you have the rate equation, then to find the average rate of change, you use the the average value function, because that average value function will give you the average value of whatever function you have. And since the function we have is the rate of change function, well then when I want the average rate of change, I want the average value of that function. So we just have here 1 over 24 times the integral from 0 to 24 of Q of t dt. And I just need to plug that into my calculator, and I believe we're going to get about 10.785. And it says indicate our units. I can think about this a couple different ways. One way to think about it is, well, you're finding the average value of this thing, and since this is Q of t, which is approximating R of t, it's got to be the same values, so it's gallons per hour. So it's the average value of that function, so it should still be in gallons per hour. Gallons per hour. Another way to think about that is if you sort of imagine that this thing here wasn't there, if the 1 over 24 wasn't there, the output of this integral would be gallons. because that's sort of your net change, how many gallons have come into the pipe, just like our answer to part A. Or sorry, have flowed out of the pipe. And then, so this whole thing is gallons, and then you're dividing by 24, which is hours, so you get gallons over hours, gallons per hour. All right, there we go.